analysis, we have a map of the interval 0, 1. Sometimes I just write I. Okay, we have full branch. C2 and with so
uniformly expanded.
yes, uniformly no, I was wondering if it needed, okay, uniformly expanding. And I had a, what was the other condition that I had there? Yes, those two conditions that we had. So uniformly expanding and this condition that gives the bounded distortion basically, right? So the supremum of the second derivative over the first derivative squared is bounded. Okay, so if, as I mentioned before, this is a fairly general situation. In some sense, the full branch is the strongest condition. I mean, the full branch is a non-trivial property. It says that you have some partition where you map each element of the partition maps bijectively onto everything. We've looked at these maps. Okay. Uniformly expanding is easy, for example, if the derivative is bigger than 1 everywhere, right? Then you have uniformly expanding. And this is something you can check. If it's got a finite number of if the derivative, the first and second derivatives are bounded above, because they're always bounded below, because the derivative is bigger than 1. So if the second derivative is bounded above, then this is automatically satisfied. Okay, so it's fairly simple conditions. And what we've shown is the theorem that there exists. What we're going to show is that there exists, so F admits a unique, I said I would prepare the statement about uniqueness. I haven't done that, I will see. Okay, F admits a unique periodic probability measure mu, which is absolutely continuous with respect to the vector. Okay, and the density H equals d mu dm is Lipchitz and bounded above and below. So if you remember, we discussed a construction where we define, we let, so as the proof, so just to remind you, we let mu n equals 1 over n, the sum of I equals 0 to n minus 1 of f star im, right? And then we write hn equals the random Nicotin derivative of d mu n with respect to m. And then we need to show proposition is that Hn, so there exists k greater than 0, such that infimum over all x and n of Hn x, which is less than supremum over x and x is less than equal to k. Okay, and Hn less than or equal to k distance between x minus y, which is less than or equal to k squared times the distance between x and y. Yes, I think this is what we had last time. So this is the main technical result which we still have to prove. What this says, as we saw last time, is that these densities, so here we have a sequence of measures that are defined dynamically starting from Lebesgue measure, M is Lebesgue. And as we saw last time, each of these is absolutely continuous. Okay, but if you remember, we gave an example to show that a priori that does not mean that any limit point is absolutely continuous. So because each of these is absolutely continuous, then it has a density. Okay, and if we have this bound on the density, then we showed last time that that means that the limit is, or any limit point is absolutely continuous. Okay, and is invariant. So all we need to show is this proposition here that shows this bound. So this shows that this density is uniformly bounded above and below. So and it's Lipchitz continuous in this way. So by Ascoli-Arzelà theorem, it has a limit. It has some limit point in the space of Lipchitz continuous functions in this way. And then we show that that limit point is the density of a measure which satisfies these properties. Okay, this was the argument that we used. And this implies, so this implies theorem except uniqueness. And I'm sorry, I forgot. I will next time I will prepare, because I can give you, I don't want to get confused, so I will give you next time the argument for the uniqueness. For the moment, let's go on and prove this proposition. So proof of proposition. Okay, so the first part is just to notice that this Hn has a particular form. So we have a lemma that says that for all n and for all x in 0, 1, we have that Hn of x is equal to 1 over n, the sum of Sn of x, Si of x, Si of x, I equals 0, n minus 1, where Si of x is equal to the sum for all the pre-images of x of 1 over the derivative in this pre-image. Maybe the index is not exactly right here, sorry. Let's take it from 1. It should be from 1 to so this should be, sorry, this should be from 1 to n. Yeah. From 1 to n. So what is this saying? This is saying that we have an explicit form for these densities, right? So this is mu n. These are the measures mu n that we're constructing. So we're trying to get a handle on these measures mu n, right? These measures are absolutely continuous by definition, so they have a density. And what we're saying is the density is exactly of this form, okay? So in fact, what we're saying is that Si is exactly the form of the density of Fi star n. Okay, because this measure is the averages of these measures, the density is the average of these densities, and this is exactly the density of Fi star n. And what does that mean? Let's look a little bit at what this says. Look at I equals 1. Okay, when I equals 1, what is this saying? This is saying take the pre-image f minus 1 of x. So this is our map f, right? And so we want to know, we want to look at this point here. This is a point x. We want to calculate the density of f star m. So we're looking at f star m, right? So what is the measure f star m? How's the measure f star m defined? Remember that the measure f star m of some set is by definition equals the measure of f minus 1 of a. Okay, this is the measure f star m. Now, what is the density of this measure? This measure is absolutely continuous, so it has a density which is h1. h1 is equal to the density of f star m over dm. Okay? And we are making a statement about the density, so I claim, sorry, S1. S1. Okay? Each one of these is the density of this f star. So, what is the form of this density? What I'm telling you is that I know exactly, explicitly, the formula for the density of this map, of this new measure with respect to this. And this is given by what? I want to know. So this is a function, right? It's the density, and it takes values at different points. So I know what is the value at this point x. Okay? And I claim, so I write x here. Okay, this is x. And I claim that the way to calculate the value of this density is exactly by looking at all the pre-images. So x has a pre-image here, it has a pre-image here, it has one pre-image in each branch, right? Remember, this is the structure of full branch maps, that each point has exactly one pre-image inside each branch. And what I'm saying is that I have here y1, y2, these are all the pre-images, y3, y4, y5. Okay? If it is a countable, it's okay. We have a countable set. And at each point y1, I calculate the derivative of the map. Right? This is y2, sorry, y2 is here. Okay? I calculate the derivative, and I take the formula, I take the sum over all pre-images of f minus 1 of x of 1 over the derivative. In some sense, that's the derivative of the inverse, right? That's the derivative looking from this direction. So 1 over the derivative is the derivative of the inverse branches at x. In some sense, as we shall see that plays the key role. Okay? So this is the first thing we're going to show, is that we want to show the properties of this Hn. Okay, this will follow by similar properties for Si. So the first thing we show that Hn is of this form, and then we prove a similar proposition for this Si of x once we have this very explicit form. Okay, so how do we show this? So the proof of the lemma. So we want to show that Six is the density. So we want to show, need to show that f I star m, that Si is equal to df I star m by dm, okay, which means that f I star m of some set a is given by the integral over a of Si dm. Right, that's the definition of the density. Okay, so we need to show this. Okay. And so we can, it is enough, as always, to check these for intervals. It's easier, and it's enough to suppose that A is an interval. If you can show that this holds for every interval, then it automatically applies to all measurable sets. And so we take some set A. So by definition, so not by definition, so now just by elementary calculus, so by calculus, we have that the measure of A, we can write the measure of A as equal to the integral over what I want to take is f minus n of A of dfn. Yeah. Right? So it's simply, I take a set A, and the Lebesgue measure of A, I can look at all the pre-images. Right, so here we'll get a component for the pre-image. Here we'll get another component for the pre-image. And you know that there's a relation between the size of this and the size of this that says that the size of this is equal to the integral over this of the derivative. Yeah, because it's pre-image. Okay? So we just take the sum of the integrals over all the pre-images. Okay, we get that. And therefore, okay, and the measure, so I'm just writing two preliminary equalities, and the measure of f minus n of a intersection omega. So if I just look at one of these, okay, then I can just write this as, I can look at the inverse map, so I can write this as equal to the integral over A of the inverse map, which is 1 over the derivative in f minus n minus I, sorry, I want I here, minus I of x intersection omega in the n. Right? So I look at one of these pre-images, okay, for omega. So this is omega in our partition element that defines the full branch map. And then we look at the pre-image of A restricted to one of these. So we look at one of the components of the pre-image, and we can write just by exactly the same formula by looking at the inverse branch on this thing, okay, that this is equal to the integral over A of the derivative of the inverse, okay, which is just 1 over the derivative of f minus I of x. So x is in here, f minus I is the point inside f minus A omega, okay, and we take the 1 over the derivative there is the same as the derivative here. So it's a bit harder to say than to say. Okay, you need to just think about that a little bit, that's what you get. You get the inverse branch here, it's just 1 over the derivative, but then since you're taking points x in A, right, this is dm of x, so you're taking points x in A, so you need to take the pre-image, and then you take all the points, as you range along the points in A, you get the pre-image restricted to omega, because this has many pre-images, and you take the derivative I there, sorry. Okay? Okay, and with these two standard equalities, then we can easily get the formula that we want. Okay, then we have f star I of A, fi star n of A. Okay, this is what we're trying to show. We're trying to show that this has exactly this form. Okay, and if you remember, the definition of this is equal to the measure of f minus I of A. Okay, and this is equal, so the pre-image of A has all these different components, so this is just the sum overall omega in Pn, in Pi, right? This is the full branch map corresponding to Fi of the measure of F minus I of A intersection omega, restricted to each omega. And now this is where we use this. Okay, so the Lebesgue measure of this is equal to the sum of omega in Pi of the integral over A of 1 over the derivative in F minus I of X intersection omega m. Okay, and this is just a sum, so this can come out. So we can write this as the integral of A of the sum of omega in Pi of this, of 1 over df in Fix intersection omega dm.
Fi or square of
F minus I. Yes. The F minus I, yes, thank you. And what is this?
This density function.
Yes, because what is this exactly? This is just the derivative in F minus I of X. So we can write this as equal to the integral in A of the sum of all pre-images of X. Right? This is exactly F minus I of X are exactly the pre-images of X. So this is the sum over Y equals pre-image of X of 1 over df of Y. Right? Because there is one pre-image inside each omega. So when we take the sum over pre-images, it's the same thing as taking the sum over all omega of this F minus Ix intersection omega is just the pre-image of X that belongs to omega. Each omega contains one pre-image of X. This is equal to this, Y, okay, and so this is exactly equal to a Si dn. So this shows, I think the intuitive way to look at it is that why does the derivative come into this? Because the derivative is telling you how the measure is stretching or contracting, is how the measure, remember in the piecewise affine case, just a small heuristic parenthesis, like in the piecewise affine case, Lebesgue measure is invariant. Right? So in the piecewise affine case, when you take f star of m, you just get m. Right? Lebesgue measure is invariant. F star of m equals m. What happens when Lebesgue measure is not invariant? Somehow, the way the measure Lebesgue is being transformed by the map is exactly due to the derivative, right? Because if the derivative is large, then somehow the mass here is being stretched. If the derivative is smaller, then the mass is being stretched less, just as a slight heuristic view, okay? So that's why it's natural that you get these derivatives coming in the density of f star m. Okay, just to get a feeling why this is not completely out of the blue. So this is just a completely straightforward, even though it takes a little bit to look through it, it's a completely straightforward one-line calculation of the derivative, just using standard calculus, right, in terms of the measure of sets and how these measures are stretched by a map, by the derivative of the map. Okay, so this proves that lemma. So now all we need to show is that this SI satisfies the properties we need, right? So now we have an explicit form and we have what we need. So what we're going to show now is that lemma is that SI, so there exists a constant k greater than 0 such that the inf of S n of x less than the sup of S n of x is less than k, okay? And we have the Sn minus Sy, where the Lipchitz condition is exactly the same as Hn, Sn of x, x minus y, less than equal to k squared, x minus y. Okay, so clearly, since Hn is just the average of these Sns, Sis, then we get the proposition. Okay? Sorry? So the key point here is that this is uniform, so these bounds, this inf is uniformly bounded away from 0, not only for every x, but for every n, right? So this is x and n, this is important. Because that's how we then get the Ascoli-Arzelà. We can apply the
So it's n or Hn?
No, our proposition was Hn.
Okay.
But we've seen, what we just proved in this lemma is that Hn, well, what we wrote, we just wrote Hn as the average of Si, right? And so you can easily check that if we prove this for Si, then we will get the same Lipchitz properties for Hn. Yes. So, and Si, we've got the explicit formula for Si now. So this is how we're going to prove these forms for Si. Okay, so this is actually very similar. I don't know if you all did this. This uses the bounded distortion. And okay, what is the, so remember that we've got Si proof. So we've got, well, let's write it as Sn. Remember that Sn of x is equal to the sum over y equals f minus I of x of 1 over dfn of x. Okay, this is the definition of Sn. So this is what we need to prove, that that is uniformly bounded. So okay, so by conditions 1 and 2, in the assumptions of f, right, so the uniform expansivity and the condition on the first and second derivative, the f has uniformly bounded distortion. Okay, this means that there exists d, exists a constant d greater than 0, such that dfn of x over dfn of y is less than or equal to d for all x, y in omega n, which is an element of Pn, okay, and for all n, crucial. So the way I write it before is with log, right? Log of this is uniformly bounded by a constant uniformly in the partition element and in n, but so this d is really exponential of the constant I had before. Okay, so I can just take exponentials on both sides and I just write it like this. So this means, okay, that if you take the ratio between the derivatives at any 2 points, it's uniformly bounded. Okay, that's one of the consequences of the uniform bounded distortion. Okay, is this. And this is independent of n. So even when you have very large iterates, so if you remember when you iterate, if this is f1, and then when you iterate, when you have fn, then it will be, right, it will be full branch maps which many more iterate, when you know, with the refinement of the partition Pn. So inside these very small elements you will have the derivative, the branch will be much steeper, so the derivative will be much higher. But even so, if you take any 2 points inside one branch and you take the ratio between the derivatives, it is uniformly bounded. Okay, that is the implication of uniform bounded distortion. So what does that mean, that this is uniformly bounded? So this is some element omega n in Pn, right? And what does that mean about the derivatives? So this says that, let me write something a little bit informally. So by the mean value theorem, we have, so the picture is the following, is that we have here omega n, and then we have fn, and then we map to 0, 1. Okay? So what do we know about the derivatives inside these points? Well, we know that if you take a point here, so we know by the mean value theorem, we have that there exists some psi in omega n, okay, such that dfn of psi times the size of omega n is equal to 1, because this is the interval 0, 1. Okay? And this means that dfn of psi is exactly equal to 1 over the size of omega n. Okay, and this means that the derivative at every point in omega is uniformly comparable to this. Okay, so every point in omega, okay, so let me write it a little bit informally here. So basically dfn of x is approximately 1 over omega n, okay, for all x in this particular omega n. Okay, and you can formalize that by saying that up to a constant d, right, so the ratio between this and this is just d, so basically this is less than or equal to d times this and greater than or equal 1 over d times that. Okay, so up to this multiplicative factor d, the derivative at every point in this omega n is given by 1 over omega n. Yes? Your question? So what do we do with this? So that means that we're basically done, because what we need is the derivative, right? So the formula for Sn of x is equal to the sum over y equals f minus n of x of 1 over the derivative df n of x of y. Okay, this is the formula of Sn of x. And what do we know about 1 over dfn of x? Exactly. Is approximately, up to some multiplicative constant, is approximately the sum over all omega n into n of omega n. Okay, and this approximately gives some bound. Okay, this is equal to 1, so this is less than equal to some constant, which I think should actually be d. Now, I wouldn't be completely sure, but I think this, well, let's write it a little bit more precisely. This is less than equal to d times that, and I think this is less than equal to d. I think it should be a guess. And greater than equal to 1 over d, right? And for the same reason, you get similarly Sn of x is greater than equal to 1 over d, right? So this gives exactly this, and this d does not depend on n, and this does not depend on x. So this gives exactly the uniform upper and lower bound here. For the infimum over all x and all n is uniformly bounded above and below. So you can see that this just follows immediately from the bounded distortion property. Okay? So now we need to prove the Lipchitz property. The fact that it's Lipchitz is really just some straightforward calculations here, although it's a little bit technical. But okay, to prove Lipchitz property, we just write, so remember that what we have, yes. So what we have is a little bit more, remember, and I emphasized when we wrote the statement that the bounded distortion property we get from conditions 1 and 2 is a little bit more, is we get, so by some lemma that I cannot remember, I did not number, but anyway, we had to prove Lipchitz, use that we have that actually dfn of x over dfn of y, log of this, we showed that is less than or equal to some constant times the distance between fn of x minus fn of y. Remember that? So we had a little bit more. So this implies in particular, so d, we can still use d, sorry, we can still use d. So we had a little bit more than this. Oh no, because this is the exponential of d. Sorry, let's just use it k. I'm mixing a little bit the two constants. So this is a stronger version because of course this is uniformly bounded by 1. Okay, so this in particular implies that this is always less than or equal to k. So taking exponentials on both sides, we get this. Okay, which is all we need for this part of the statement. But for the Lipchitz property, which is a stronger version, we do need this stronger version of bounded distortion that says that not only this is uniformly bounded, but there is a specific bound that is uniform in the distance between x and y here. Okay? So, when we use this, taking exponentials again, this gives df n of x over d fn of y less than or equal to exponential times k fnx minus fn of y. Okay, and I'm going to write this as less than or equal to 1 plus some k tilde times fn of x minus fn of y, right? Because the exponential of something is less than or equal to 1 plus x. Exponential of x is less than or equal to 1 plus x. Right? Sorry, this is because this is small. Okay, this is true because this is small. Okay, since fn of x minus fn of y less than or equal to 1. Okay, then we have this. We can write it like this. And okay, and then here inverting x and y, so this implies also, so inverting x and y, from this we also get that df n of y over df n of x is greater than or equal to greater than or equal to this, greater than or equal to 1 over 1 plus k tilde fnx minus fny. Right? So directly from this, we just move everything to the opposite side, and this we can write as greater than or equal to 1 plus 1 minus k double tilde fnx minus fny. So all I'm trying to do is get upper and lower bounds. Okay, so I'm saying that here, using the bounded distortion and taking exponentials, we show that this is less than or equal to 1 plus something that depends on f and x, y. And because of this, because this holds for every x and y, or well, just taking this equation and taking everything to the other side, we get this. And using this, we can show that this has a lower bound, which is of this form for some different k, right? For some different k. So here I'm just introducing for some k tilde and some k double tilde. And
This is the same k.
two different tildes. It doesn't matter. It's just some constant, right? So this is a k. This is This is also k. Let me call this k1, 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 and k2. So there exists k1, k2 greater than 0, such that this holds.
But the first inequality is not true if k1 is the same situation, because if we use Taylor exponential or Taylor series, in this case this is the first two terms of.
You're right. We just need some.
But if this is model is smaller than 1, so in this case for some k2 maybe bigger than k1.
Yes. You're right. So there exists. So this is the. Yes, there exists k1, k2, k3, k1, k1, k2. Thank you. K3. Yes, these are all just constants that do not depend on x and n. That's the key point. Okay, but we just want some constants that do not depend on that. Okay, so we have here what we had before was just saying that this is uniformly bounded above and below, this uniformly bounded above for any x and y, and here we, using this stronger bounded distortion property, we get bounds above and below in terms of fnx and fny, which is this. Okay, and this in particular implies that combining these and letting k equals the maximum of k2 and k3, okay, then this says that basically this is telling you how close we are to 1, right? This is an upper bound saying that this is less than or equal to 1 plus something, this is greater than or equal to 1 minus something else, so we can just write this as df n of x over dfn of y minus 1 is less than or equal to k fnx minus fny. In fact, I realize now that I think we already had shown this, basically, that the bounded distortion, that this is the bounded distortion we get with those two properties, if I'm not mistaken. So this is just a few steps to show that in fact from this bounded distortion we actually get this, okay, which I think maybe we had already. Anyway, this is the property we need. Okay, this is the actual property we need to end up with this. And so now, what we will write now, so we estimate what we want to estimate here, Snx minus Sny is equal to the sum of y equals f minus n of x of 1 over the fn of x, of y, okay? Here I'm using x, y, wait. Sorry, so let me write, so this is x and this is y, so here are the pre-images, let me write this as x tilde in the pre-images of x minus the sum over all y tilde, which are the pre-images of y, of 1 over df and y tilde. Okay, so these are just the definitions of Sn and Sny. Okay. And this I can I'm going to index this. Yes. So I want to combine these two, so I want to make sure, I want to basically write these in a single sum, right? So I can do that by choosing always the same pre-image in the same branch, right? So let me write it like this. So this is equal to the sum I equals 1 to however many branches I have. Let's assume we have an infinite number of branches, so to make sure it works. If we have a finite number of branches, then we just index them like this, right? We do up to time n, up to n. And here we write the fn of xi, okay, where, and let me write it in the same way, I equals 1 to infinity of 1 over the fn, x tilde I, or I can just write xi, yi, okay, where xi is equal to f minus n of x intersection omega n I, right, and yi is equal to f minus n of y intersection omega and I, and omega and I is some indexing of omega n in Pn. Okay, so because here I'm taking the set of all the pre-images, I'm taking the sum, I'm taking the set of all pre-images, I'm taking the sum, but of course each pre-image belongs to one omega n, okay? So this way I fix some indexing of all these omega n i's, okay? And then I can make sure I can write this in such a way that I'm taking each xi inside the same omega I. So this means that here in this sum, this xi and this yi belong to the same omega ni. Okay, so It is just a little technical issue here. Okay? And so this means that I can write this. I can take the absolute value inside. I can put less than or equal. I take the absolute value inside and I can put this all into a single sum. So this gives the sum I equals 1 to infinity of the difference between these two. Okay, 1 over dfn xi minus 1 over the what's happened to it? Okay, I also have them here. Dfn yi and this I can write as equal to the sum I equals 1 to infinity of 1 over, so I can just put this into a single, so well I can write it as 1 over dfn xi times 1 minus dfn xi over dfn y. Okay, that should be right. So okay, and here now I have on this side I have the estimate that I want, so I have an estimate for this, right? So this is less than or equal to k, right, which is that, times the sum, because I'm going to bound this by that, so this is the sum I equals 1 to infinity of 1 over dfn xi times the distance between fn of xi minus fn of y. Okay? And this here is exactly the sum over all the pre-images of x, or 1 over the fn of x, right? So this is exactly equal to k Sn of x fn of xi minus fn
But
of y.
maybe we need to take maximum or minimum, maximum supremum of fn xi minus fn yi, because xi is omega I in each branches and different points.
Sorry, say again.
So this is a fn xi minus fn yi belongs to sum, inside sum. This belongs to inside sum, and so we need to take some, is this maximum or something? We need to estimate this first.
Oh, you mean here?
Yes. This is because this is also inside sum. This one.
Oh, this is inside the sum.
Maybe.
Wait, yeah. That's true. That's inside the sum. Well, but it's independent of the sum because f of x. Yes, so you're right. Okay, but this. Okay. So this is x, y. This is the distance between x and y. So this is equal to k I equals 1 to infinity of 1 over dfn of xi times x minus y. Yes, thank you. To be correct is that. And this is exactly equal to k Sn of x times x minus 1. Yes. Which is exactly what we wanted to show. Okay, so we've shown that these SNs satisfies this boundedness and Lipchitz property, so the HN2, so the family of those densities Hn are equicontinuous, as we discussed last time. They form an equicontinuous family, so we showed that the limit is absolutely continuous and it's invariant, and therefore we have an absolutely continuous invariant measure. Okay, next time I will mention the uniqueness because I want to prepare it properly so you don't get confused. Okay, so let's just take a couple of minutes break and come back. Okay, so I think we've, as I said, this theorem about the existence and ergodicity of absolutely continuous invariant measures for these full branch maps with bounded distortion is somehow the main theorem of this second part of the course. So we've completed complete proof of this theorem in all the details. In the remaining part of the course, which is the end of this lecture and 2 more lectures, I want to talk a little bit about how to extend beyond the uniformly expanding case, because these are quite special. In principle, we'd like to extend beyond the full branch, beyond into higher dimensions and so on, but we need to take some little steps at a time. Okay, so I will, for the moment, just look at some more one-dimensional maps. Let me look at 2 examples, give 2 examples. One of them is the following example: x plus x alpha mod 1 for some alpha in 0, 1. Well, for the moment, let's just say for some alpha greater than 0. And what does this map look like? What does this map look like? So at 0 is equal to 0, right? At 1 it's equal to 1. Well, at 1 is equal to 2 mod 1 is equal to 1, okay? But the fact that it's equal to 2 gives you a clue, right, as to what it's going to look like. It's basically going to have 2 branches, because as you go from x, this is monotone increasing, so as you go from 0 to 1, it goes up to 1 at some point, right? And then there is some point p where it's equal to 1, and then it goes up to 2. So it's going to basically have 2 kind of branches, like this and like this, okay? Is it expanding? What is the derivative of this map?
1 plus alpha.
Exactly. So f prime of x is equal to 1 plus alpha x alpha minus 1.
It depends on alpha bigger than 1.
So there is some dependence on alpha, which we will see, okay, what effect it has. So what effect does it have? So when x equals 0, what is the derivative here? Is 1. And when x is bigger than 0,
Bigger than alpha bigger than 1 to greater than 0.
so alpha, let's see, when alpha is less than 1, this is,
Negative.
At 0.
At 0 is not acceleration.
no, so at 0 this is always 1, the derivative, right? This is always, well, okay, so maybe we want, so maybe we want alpha
Alpha is bigger than 1.
greater than 1 here. So what conditions do we want? Because yes, so let's take alpha bigger than 1. Let's take alpha greater than or equal to 1. Let's take alpha greater than 1. Yes, so let's take alpha greater than 1. So there will still be an interesting dependence on alpha. So here we have the diagonal. Okay. So this will have 2 branches, and the derivative here at x will be 1, and for every other x it will be bigger than 1. Yes? Because it's 1 plus alpha something bigger than 0, right? So this is 1 plus something everywhere. Okay? It will be bigger than 1 everywhere, but it will be 1 at 1, right? So it will look something, so here it is tangent to the diagonal. It looks something like this. So it's full branch, it has 2 branches. Is it uniformly expanding?
Except 0, yes.
Well, yes or not, because accepted 0 is accepted 0. It's uniformly expanding, needs to be uniformly expanding everywhere.
We restrict to the interior of the branches.
Well, no, because even in the interior of the branches you have points that are arbitrarily close. The derivative is arbitrarily close to 1. And the uniform expansion would need the derivative to be strictly bigger than some lambda bigger than 1. Okay? Or for some iterate of the map, it needs to be uniformly expanding. Is some iterate of this map uniformly expanding? So this has the full branch structure, so the iterates of the map will still have the full branch structure because that's just a topological property, right? So if we take the second iterate, remember the construction we did, so we will get 4 branches, right? Will that second iterate be uniformly expanding? So the derivative at 0 is equal to 1. The derivative at 0 is equal to 1. So what's the derivative of the second iterate at 0?
1.
Is also equal to 1. Okay? So the derivative of every iterate at 0 is equal to 1. Okay? Because it's a fixed point, the derivative of every iterate is still 1. Okay? So we cannot iterate away this problem. Okay? This is very different from the Gauss map. If you remember in the Gauss map, there was a point with derivative 1. Okay? But it was quite easy to see that the second iterate of the map was uniformly expanding because this point with derivative 1, it mapped all the points near this point, they mapped somewhere where the derivative was large, so the second iterate was uniformly bounded away from 1. But in this case, we cannot do that. So here we have uniformly expanding. So for every iterate of the map, we will have our partition Pn, and all the partition elements will be uniformly expanding except this one. This one that contains 0 will always have, the graph will always be tangent to the diagonal here. Okay, even though the derivative will be very large because you have, because of these intervals, you know, in the partition you get defined, you get the partition Pn. This one here, the derivative will always be equal to 1. Okay, so this map does not have bounded distortion. We cannot, because if you think of this partition element, however small it is mapping this interval to everything here. So there must be some points where the derivative is very large, okay? But there's always one point where the derivative is 1. So if you look at the ratio between the derivative at 0 and the derivative at some other point in here, it blows up to infinity. Okay? So this map does not have bounded distortion. F does not have bounded distortion, which means that we cannot apply our amazing theorem that we spent so much time proving, even though it looks so close. Okay? Does it have an absolutely continuous invariant measure? We shall see. Let me give another example, which is this map here. Okay? So this case, we looked at it, there was one specific case, we looked at f of x equals, which form did I write? Maybe 2 minus Did I write it like this? I think we looked at one. There's several ways of writing it. There are 2 minus x squared. So this is actually a map, I think, between minus 2 and 2, but it's the same. So this is also full branch. And do you remember what we showed about this map?
Yeah, it's that point is
We proved that it is smoothly conjugate to the 10th map. Maybe I put x squared minus 2. Maybe I wrote it in a slightly different way. Like this? Ah, sorry, I wrote it, it's the same, it's exactly the same, but maybe I wrote it as, did I draw it like this? And I wrote it in that case x squared minus 2, I think, maybe. Yes? Anyway, it's exactly the same map, okay? And in this particular map, I pointed out that this is also full branch, but this is also not uniformly expanding because there is a point where the derivative is 0, in fact, right? So, in fact, for every pre-image of this, if you look at the orbit, you look at the orbit, the derivative along the orbit, at some point it might hit 0 if it's in the pre-image, and therefore the derivative will be 0. It cannot be uniformly expanding for all points. In this particular case, we showed that there's an absolutely continuous invariant measure, absolutely continuous, because it is smoothly conjugate to the 10th map. Okay? That is a very special case. But suppose we change this map just a tiny little bit, okay? So I just change it here. Okay? So this is no longer, this is kind of almost that, but not that. A very small perturbation. Then it is no longer conjugate to the 10th map. Right? Because the conjugacy depends on the fact that we have exactly this. Okay? And of course, the previous measure, that was absolutely continuous invariant measure for this map, will no longer be for this map. Okay? So that argument, the conjugacy was just very specially worked for this map. Okay? For this particular map. So what I want to do now is I want to show you for the rest of today and next week, a very interesting and powerful technique to extend our results to these 2 examples and many more. Okay? For showing in which cases these examples have also absolutely continuous invariant measures. So we can extend our results. We can extend our results by a method called inducing. And I will explain what it is. Sorry?
No, I think we have seen this 10th map we constructed one measure, it does parallelistic measure in 10th map, and we prove this equity.
Exactly. For this map here.
Yes.
Yes, but my comment is that that works by some just miracle, because it just so happens that this exact map is conjugate to the 10th map. But if we take even a small perturbation of this map, just make a very small change, then that conjugacy is no longer true, no longer applies. So we don't know now, after this perturbation, we no longer know if this map has an absolutely continuous invariant ergodic measure. Okay? So this is just a comment to motivate a new technique that I'm going to describe, which will allow us to deal with this case that is not uniformly expanding, and this case, not only in this particular case, but it's a much more robust method, so it will work for some perturbations of that. Okay, so it was just a motivation for that. So this method is the following. I'll first do it schematically, and then we'll try to do it in this case. Schematically is the following: is you have a dynamical system f of x to x, right? And you don't know how to study it. It's very complicated. In some sense, these are complicated because they do not satisfy the assumptions that we like. And you can take some subset, okay? Take some subset of delta x, okay? And suppose that this subset, each point in this subset, after some time comes back to this subset. Okay? Let tau be a function on delta, okay, such that f tau x of x belongs to delta. Suppose there exists such a point. So x0 is here, so x is here, and then maybe f of x comes here, and then maybe f2 of x comes here, then maybe f3 of x comes here, and then maybe okay, at some point f tau of x comes back inside delta. It's a return map. It's supposing that you find some region where all the points come back. Okay? Then we can define what's called the induced map. Then we can let f delta to delta be f of x equals f tau x of x. So now I'm defining a map from delta to itself using this return time function. Okay, this is just a map from delta to itself. And this seems like a very elementary thing, and it's very natural. And it turns out that sometimes this map is much better than the original map. So maybe I can say some things about this map, delta to delta. For example, maybe this map is uniformly expanding with bounded distortion full branch, even though the original map is not. Okay? And let's give the example of this construction here. Okay? So here I'm going to choose this map here, this delta here.
Sorry, why are we restricting the domain to delta?
Sorry?
Why are we restricting the domain to delta?
Because we are hoping that this induced map is going to be better than our original map, right? We don't have much, so we're trying to study this map here, okay? And this map, unfortunately, does not satisfy our conditions because it's got a fixed point that is 1. Okay? So now I'm going to define an induced map on a subset of this domain. Okay? And in this particular case, I'm going to define delta is equal to the interval P1 here. Okay? And I'm going to do a similar construction. Here I just defined the inducing in a very abstract setting. And here I'm going to define a map, an induced map from delta to delta. And then I'm going to try to look at the properties of that map. Okay? For the moment. And then we will see what we can do with that. But first let's see what happens when we okay, maybe I should, to give you a little bit more motivation, let me say this, that if I don't want to write this now, but if we can show that this map, okay, let me write down the formula. So what we're going to show later, let me write down this result so it's easier, is that if okay, let me write it down informally. If there exists a ergodic invariant probability measure mu hat for F invariant, big F invariant mu hat on delta. Okay, then we can spread this to get an ergodic invariant probability on X. Okay, this is the basic philosophy. So the basic philosophy is we don't know how to treat the original map F, okay, but we can find, it's not always easy and it's not always possible, or it's often possible, some subset, and we can find some induced map on delta, and we get a new map from delta to delta, and maybe this map is better, okay, and suppose that it's so good that we can apply our methods. And so for this induced map, we can find an F invariant, big F invariant, so a map that is a measure, probability measure on delta that is invariant by this induced map, and it's ergodic. So we have a new dynamical system that is from delta to delta. And then there is a standard way, which I will tell you next week, where we can take this measure and we can use the dynamics to spread it out. We basically just take these points and we spread out the measure in a standard way, and we end up with an ergodic invariant measure for little f. And that's how we construct the measure for little f. Okay, so this is, so I don't know if it was your intention or not, but you managed to make it so that I don't think I can do this construction now. Okay, so maybe we will postpone that anyway. This, I just want to introduce the general philosophy. Okay, so what I want to do in the next 2 lectures is to construct such an induced map in these 2 examples, both in this example and in the example we looked at before. Okay, so to show that even though these 2 maps are not full branch and uniformly expanding, we can find some subset. In this case, the subset will be here. In this case, the subset will be something here, some neighborhood of the critical point, okay? And we can define a map, return map, just like that. So we look at these points and these points here. So for example, this point, it maps to here, and then it maps here, and then it comes back, okay? And we define an induced map from delta to delta. And in both cases, this induced map will be full branch, uniformly expanding with bounded distortion. Okay, so we will then be able to get an absolutely continuous invariant measure using our theorem that we just proved for the induced map, and then there is a general technique that will allow us to take this measure and spread it out to the whole system. Okay, and get the measure for that. So this is the technique, and this is a very powerful technique. Yes.
So we can, if we can find such kind of delta, so we can construct. Can we find such kind of delta for every dynamic?
That is a very good question. So in fact, this is, in some sense, research. So one of Carlos mentioned this paper that we just finished. One of the corollaries of the construction that we do in higher dimensions is that if you have an absolute, if your system does have the measure you're looking for, then in principle this measure could always be obtained by such system. Okay, so this system is general. That does not mean that you always can do it, in the sense that it does not mean that you always know how to do it given a system. But what we show is that in principle you could, right? So if the system does have an absolutely continuous invariant measure, then this invariant measure has inside the system there is such an induced map that has this good, that is full branch. In some sense, this works also in high dimension. In fact, in the result for absolutely continuous measure is a paper that from several years ago, and this new paper looks at situations where you have some expanding and some contracting directions for diffeomorphism. These maps that we're looking at are all non-invertible maps that just have expansion, right? When you go into higher dimensions, you have two ways to go. Either you can continue to have maps that are expanding in every direction, okay? And these maps must essentially be non-invertible because they're expanding, so you must have some non-invertibility in the system. Or you can have diffeomorphisms where maps have some contracting, some expanding, and some contracting directions. But the basic ideas and philosophy are very similar in all these cases, actually. Okay? So this inducing, that's why I'm very happy. In other years, sometimes I've not been able to get to this stage, but what we'll do in the next couple of lectures is to explore this technique, because it kind of justifies all the work we did. You know, I insisted many times that these full branch uniformly expanding maps are very special. Okay, but I promised you that they're not so special, because what we're showing here is that in fact in many systems which do not have satisfied those properties, you can actually construct an induced map that does. Okay, and that becomes really fundamental techniques for extending these results to much more general maps. Okay, and as I said, our results show that in principle this is a technique that does work every time it can work. Okay, although if I give you a specific system, it's often not easy at all to construct this induced map in the right way. Okay, so I think that's good in some sense that we will postpone this construction, and then we can do the construction and show that what we get is uniformly expanding full branch. Okay, thank you.